Okay, so for gas stoichiometry, we've already done a little bit of this on the worksheet that you picked back up today with the density and molar mass of a gas. So that's going to show up again today on your worksheet. We also already saw the molar volume of a gas, the 22.4 liters per mole. But what you don't understand, or what we haven't really talked about, I've just given you that conversion factor in the past to use, especially in the stoichiometry unit. But it's called the molar volume of a gas, because it's the volume of 1 mole, molar volume, okay? And it does not depend on the identity of the gas, as we saw, because we said that 22.4 liters per mole is for any gas. It actually depends on the temperature and the pressure. So temperature and pressure, okay? And you can calculate the molar volume at different temperature and pressures, and it becomes a different number other than 22.4. But I would prefer you just use the ideal gas law instead of, because then once you start calculating, excuse me, other values for the molar volume of gas, then oftentimes kids forget the 22.4 or they get confused. So I just want you to remember that at standard temperature and pressure, you're going to use the 22.4 liters per mole. Okay? So that's the molar volume at STP. Okay? So if we're doing a stoichiometry problem like on our packet yesterday or our worksheet yesterday, and it says at STP, we do our little happy dance, because that means we can go straight into the 22.4 liter. We don't have to do extra calculations. But if it is not at STP, you're going to do number 4. So this is the part I'm going to have you change in your notes. So not at STP, okay? And this is supposed to be at, not, okay? So if you're not at STP conditions, you're going to do the problem one of two ways, okay? You're either going to start with your stoichiometry problem, use your stoichiometry to solve for moles of the gas you're looking for, and then you'll throw that moles of gas into the ideal gas law and get volume, okay? Or you will start with your ideal gas law, solve for moles, and then you can do your stoichiometry. So obviously we're going to do some examples. Yes?
So we got to cross out the 4 that we have there. Like,
yeah, cross out your 4 and put this in. So I'm going to pause for a second and let you guys have time to write that in. Okay, so let's work this problem. This is one that is at STP, standard temperature and pressure, the magic words or the magic letters. So we will be able to use 22.4 when we see that. Okay, so we're starting, it says what volume of hydrogen is produced by the reaction of magnesium with excess HCl. So let's go ahead and do magnesium, write out our equation. What kind of reaction is that? Single replacement. So we're going to get magnesium chloride plus hydrogen gas. And in order to balance that, we're just going to throw a 2 there. Okay? So we're starting with the 36.5 grams of magnesium. Who's going to be my calculator today? We're going to divide by moles, not moles, grams, so that we can convert to moles. Then we're going to use our mole ratio. 1 mole of magnesium will produce 1 mole of hydrogen gas. And because we are at STP, I can say for every 1 mole is 22.4 liters of any gas, right? So, who's my calculator today? Who actually has one out? Thank you, Adam. Okay, so say 33.6. We need 3 sig figs because of that right there. So it would be 33.6 liters of hydrogen would be produced from this reaction at standard temperature and standard pressure. Okay, so now we're going to do the same amount, 36.5, but we're going to do it at non-STP conditions, and you'll see it's a different value. Okay, does everybody have this before I move on? I'm trying to write slower. I know sometimes I write too fast. Okay. So what volume of hydrogen is produced by the reaction? Same amount of magnesium, but now we're at these conditions. Okay. So, oh, come on. This thing just decided to stop working. Okay. So now we have 25 degrees Celsius, and so that would be, our temperature is going to be 298 K when I add the 273. And then for pressure, you're going to do 730.5 divided by 760, and that should give you 0.9612 atmosphere. So we're going to need to use that in a moment. Okay? But the only thing we can actually start with at this time is the grams. So we're going to start with our grams, 36.5 grams of magnesium divided by the molar mass. I'm writing fast again, aren't I? Sorry. It's because I can do stoichiometry problems in my sleep.
Thank goodness we can too.
So we have 1 mole of magnesium is equal to 1 mole of hydrogen. Okay? That is where we're going to stop our stoichiometry problem, because we're going to take the moles of hydrogen and now plug it into our ideal gas law. So let's calculate that and tell me how many moles we get. 1.5 moles. Is it 1.50 or is it just 1.5? Okay. So that's moles of hydrogen, but it wants volume. Well, we're not at STP, so we can't do the magic 22.4, so no happy dances here. Okay. So now we're going to use our ideal gas law, PIV-NERT, and solve for volume. So now we'll put 1.50 moles, our 0.0821 liters atmosphere over mole K, our 298. Divided by our pressure, 9612 atm. So we throw all that into our handy dandy trusty calculator. And Adam tells us, Adam or Blake, because Blake gave us the last number. Oh, Lauren has it. Oh.
How did you get that 1.5?
Right here, stoichiometry.
Oh, that's just divided out.
Yeah, I just got, yeah. Just like what we were doing from the stoichiometry, we just stop at moles, because we're going to take that moles and plug it into the ideal gas law now. Now before, I did the 22.4 and kept going because I was at STP, but because I'm not at STP, I can't do that. So now I'm going to plug it in here. And what did we get? 38.2. And that is liters of hydrogen. So same amount of magnesium as the previous problem, but look, we got like almost, not quite 5 more liters at being at different conditions. Okay? So I really kind of want to, that's if you start with grams and need to go to volume. There's not one in your notes of going from volume and going to grams, so I'm going to make up a problem. So if you have a spot you want to write it, or if you just want to watch, I would, most likely I would write it down because you might see one like this. No, this is from grams to volume. This went from grams to liters. Okay? Because we started with grams, and then we ultimately needed volume. So I would like to do one that's going to be opposite. It's going to give you a volume, and it's going to want to go to grams.
Are we still going to do the PIV-NERT thing?
Yes, but this time you're going to start with PIV-NERT on the new problem. Okay? So let's make up a problem. Let's do some decomposing of calcium chlorate. And it's going to decompose into calcium chloride. I'm making this up, and oxygen. So I need to balance that by putting a 3 there. Okay? I'm going to give you, we're going to say our given is that we formed 8.7 liters of oxygen. This thing is acting crazy. It's been doing this. I hope my projector is like not about to go out because it keeps doing this. So then I want to know, whoop, we want to know how many grams was originally decomposed. So that's what we're going to look for in our made-up problem.
For calcium?
For calcium chlorate. I'm pointing to the whole thing, not just calcium, because the calcium's not decomposing, the calcium chlorate is decomposing. So this time, since I have volume, I can't start with my stoichiometry, so I'm going to start with my pivnert, and I'm going to solve for moles. So it's going to be N is equal to PV RT. And I need to give you some conditions. I didn't do that. Okay? So conditions not at STP are going to be, let's go with 28 degrees Celsius. And let's go ahead and keep it easy and say 1.9 atmosphere. So 28 degrees Celsius is going to be 301 Kelvin. Yes? Okay. So we're going to throw everything in and solve for moles. Okay? So we have the pressure of 1.9 atmosphere. Our volume was 8.7. Divided by R, always the same. And then our temperature was 301 K. So who is going to calculate that? What you got? Point six. Well, we're going to do 6.7. Okay, so 0.67 moles of oxygen. We are not at calcium chlorate yet. We are at oxygen. We turned volume into moles of oxygen. So now I can go down here and say 0.67 moles of oxygen, and now I can do my stoichiometry. 3 moles of oxygen give me 1 mole of calcium chlorate. And then to get to grams, I would say 1 mole of calcium chlorate. I'm going to need someone to give me a molar mass. Is, I think it was 206 something grams. But I'm going by memory, so that could be a problem. Was it 206.98? Someone... Yeah, 206.98 for my molar mass. Then I multiply... And I think I got 46.2, or in this case 46 because I only need 2 sig figs. So 46 grams was originally decomposed. Did someone else get that number? Because I'm... Yes?
How did you know that whenever we got the moles that it's oxygen?
Because the only thing, what we plugged in was liters of oxygen.
Oh,
We didn't do anything to convert out of oxygen.
I didn't know that was.
I didn't know that the
Oh, given 8.7.
Yeah, of oxygen. I wrote it under it, so yeah.
It doesn't say.
Yeah. Well, can I get liters of calcium chloride? Not as a gas. I could as a liquid, but then I can only put gases into the ideal gas law. Okay? All right. So any questions on gas stoichiometry before we go on to effusion and diffusion? Okay? All right. Then let's move forward. All right, that brings us to the last part of this notes, which is effusion and diffusion. Okay? So we're talking about how the gas particles behave, and invariably on a test they get them backwards, so make sure you get them correct. Okay? So diffusion is the gradual mixing of 2 gases due to their spontaneous random motion. You can also have diffusion of liquids, but we're not talking about liquids, but in diffusion of liquids, if I were to take, say, a big tall container of water and I put a drop of food coloring, you would see it like moving, but eventually it would all be the same color. It just takes a lot longer. Diffusion happens very rapidly, and it's because the gas particles are moving so fast. So examples of that is why we can smell perfume when they spray it, or if someone burns the toast or burns the popcorn, you can smell it all over the building, right? It's also the process of how air fresheners work, is the particles are diffusing, and your nose just happens to be very sensitive to certain molecules, okay? So diffusion is when it spreads out and fills a room, okay? If I were to go back there and turn on the gas, it wouldn't take us long to smell it throughout the whole, not only here, they'd start smelling it across the way, okay? So that is diffusion. It happens quickly because of the air particles moving so rapidly, so it doesn't take it very long. Effusion is the process by where gas molecules in a container will pass through a tiny opening in the container. Best example of this is getting a flat tire. If you get a hole in your tire, what happens to the air? Okay, it effuses out that little pinhole from the nail or whatever poked your tire, and then you have a flat tire. Okay.
Same thing like a balloon.
That is the same thing like a balloon. For instance, it's like you knew that was there, Hussein. Helium effuses out of a balloon faster than just air because it's lighter and their particles are smaller, so it fits through there, especially your standard normal balloons. Mylar balloons are a little bit different because they're a different material. That's why Mylar balloons hold the air so much longer than just a standard regular old run-of-the-mill birthday party balloon. Okay. So you have to effuse before you can diffuse. Okay? So effusion has to pass out of the opening before it can diffuse. In the case of perfume, that opening is when we spray it out of the container, or if it's a roll-on or whatever, open it up. Okay? You got to effuse before you can diffuse. You can figure that one out too. Okay? Oh, okay. So that brings us to Graham's law, and Graham's law is governing the rates of diffusion of gases. Okay. So at the same temperature and pressure, they are inversely proportional to the square root of their molar masses. So it looks like this. So let's say we have the rate of A over the rate of B. It's going to be equal to the square root of the molar masses of the inverse. Okay? So we'll do two examples of that. That's mm is molar mass. Okay? So, but basically, the lighter it is, the faster it's going to effuse, which makes sense. Their particles are lighter. Okay? Now, it doesn't have to do with their kinetic energy, because honestly, it's weird for some kids to grasp, but the kinetic energy of any gas at the same temperature is the same. I can have 10 gases, and if it's the same temperature, they're going to have the same amount of kinetic energy. That is not the same as their velocity or their speed. That will be based on the lighter the particle, the faster they move. But their kinetic energy would be the same. Okay? So let's do an example of this. I already gave you that general equation. So here we're going to compare the rates of effusion of ammonia, which is NH3, and hydrochloric acid. And we're going to need their molar masses. So ammonia is going to be 17.04, and this is 36.46. And it wants to know how much faster does ammonia effuse than hydrochloric acid. So we're going to say rate of NH3 over the rate of HCl, and we're going to do the square root of their molar masses inverse. So you throw that in your calculator and you should get 1.463, so basically 1.5 times faster. So ammonia will effuse 1.5 times as fast as HCl because it's lighter. Yes?
So you put like the bigger molar mass
Not the bigger, the inverse. We were wanting to compare ammonia to HCl. So we put ammonia on top because we want to do the rate. And then the formula is an inverse of their molar masses. It just so happens yeah. So it's not always the bigger one on top. You have to read the question and know what it's asking. And then sometimes it will tell you, the next one, it's going to tell you how much time faster, and it wants you to figure out what the gas is. Okay? So let's do that last problem, and then we are done for the day. Well, at least with notes. You're not done for the day. We're done with notes. Okay? So this one says nitrogen gas, which is N2, which means it's going to have a molar mass of 28.02. That caught a lot of people on the worksheet. Got to double the mass for the Brinkelhoffs. Fuses through a pinhole 1.7 times faster than another gaseous element, okay, at the same conditions. So what is the other element's molar mass and identity? So we're going to say rate of nitrogen over the rate of X, because we don't know what it is, equals square root of the molar mass of X over 28.02. It tells us in the problem that that was what? So that's all equal to 1.7, right? Which is this value right here. If I want to get rid, I'm going to do this in a different color. If I want to get rid of square roots, what do? Square what? Both sides. So square both sides. And then I get X over 28.02 is equal to 2.9. So then I get X is equal to 81.3. So find the element that has the closest molar mass to that. Krypton, yes. Krypton. Why is it not bromine?
Because bromine's a liquid.
Because bromine's a liquid. That's the main reason right there. Mm-hmm. Mm-hmm. It's also Br2. That's another way to look at it. But a lot of people just look up there and saw that. And chlorine wouldn't work either because it's diatomic and it would have 70, which is less than that. So that's how you do that. Okay? All right. The end.